So far what we have done is we have covered random variables. So in random variables, we saw that there is associated PMF and CDF. Then we saw a lot of types of random variable. The first thing we saw is Bernoulli random variable. We saw binomial random variable, then a hypergeometric random variable. With those random variables, we also computed their PMFs and then CDFs. And then we also read about expectations. Then we computed the expectation of Bernoulli and binomial, and this homework for you. Now today we are going to shift our gears and see other distributions, other discrete random variables, the discrete distributions, which will be used almost each of the distribution will be used in machine learning or deep learning in one way or the other. So the first distribution, and that is geometric random variable, geometric distribution. So what is this geometric random variable? So we have seen an example, an experiment of that sort. I said, if let's suppose we have a coin, if we flip this coin continuously, let's say we consider head to be success and tail to be a failure. And if we keep on tossing this coin till one head appears, we'll stop only if one head appears. That means till we don't see a success, we will keep on tossing the coin, something like that. So this will form a geometric random variable. Okay, so the geometric random variable. So in this, we perform these independent trials, and each having the probability of success is p. So here success probability, I'll write it p, and failure probability 1 minus p, or we can write it q. Okay, and then we perform the experiment until the success is reached. And it is defined sometimes in a different way. Sometimes some books define it. Let's suppose if this x is a geometric random variable, some books will define it as number of failures before first success. Or it might be defined as failures. Basically, the last toss is also taken into consideration. Failures until the first. So in the first case, you drop out the last one, and in the second case, you basically also count that one. So anyways, it does not have any difference on the results. So notationally, they remain same, and every formula probably remains the same. Then if you sort of derive formulation for one thing, it automatically can derive formula for other thing also. You have to model the problem accordingly. So you might see two different things if you go on different books. So you'll see that sometimes they are considering one less, and some books are considering one more than others. So it's basically in these words: number of failures before first success, or something as in number of failures until the first success happened. So how many failures did happen until the first success was? Now whenever I say something about any random variables, the first thing that should come into your mind is how to now compute probability mass function of this. In order to define a distribution, so we should come up with the probability mass function. So here I told you this geometric random variable is a random variable, so in which what we are doing basically is we are trying to compute the number of failures before the first success. So how many failures it can be? So there can be 0 failures. Let's suppose on the first try itself you saw it head in the coin toss, and there can be one failure, and after one failure you got a success. There can be 2 failures, and so on. So these are the possible values which geometric random variable will take. Now in order to define its PMF, I have to give you a function which will assign some probability to these. Any questions till here? How to compute that? If I have to say, if I write like this, probability x takes value k. So what's the meaning of this? So this means probability that there will be k failures before the first success is observed, something of this sort. So I'll assume I'll take this last. I'll not consider last. If I have to consider that, I'll either add one. If I don't have to, I'll do the minus one. So we'll have to do the exchange. So in order to abide these notations, that we'll see separately if we have to do that. But here I'll consider the probability x is equal to k. So that means that you have k failures until the first success. So the probability of failure is this much. If you see, the probability of failure is 1 minus p. If I have to write it, so I'll say 1 minus p is the probability of failure. So how many failures have observed? I'll observe k failures until the last success. So I'll write the last success. Okay. So this over here will give me the PMF. This will give me probability mass function. So let's suppose probability of x is equal to 0. If I write probability x is equal to 0, so what's the probability of this? I can just say probability 1 minus p is for 0 multiplied by probability. Similarly, probability x is equal to 1. just put the values. Means 1 minus p to the power 1. This will be qp. So you can compute the PMF. Here this is probability mass function of geometric. So other formulations I said, let's suppose if I have to write probability of x is equal to say k. So in some other books you might see that one less is counted. So they'll say that 1 minus p, 1 minus p, 1 minus p to the power k minus 1. They'll write something of this sort. They'll say that till k minus 1 we had failures and last success is counted basically in this. So here as I said, sometimes last success is counted. Last success is also counted. So how many tosses it took basically. So here when probability of x is equal to k, you might also see in some books written as 1 minus p, k minus 1 multiplied by p. So we'll follow this convention. We'll follow this PMF. So we'll not consider the last case. We'll also consider that the k failures and then we got a success. In this case, when we are saying the 1 minus p, so last we're considering that success in those. So if we have n trials, we are considering the n in the last trial is our success. So here we are considering how many failures are we getting till we are observing a success, and we are not taking that into consideration. Okay, but you might see this alternate formulation written. There's not much difference here, so you'll have to just adjust things. So once we know about random variable, we know about a PMF. So you know how to compute CDF from PMF. Now we also know how to compute expectation. We'll compute the expectation. So what is expectation? So what is the value that I can expect? So if a process follows, let's suppose, geometric distribution, what's the value that I can expect? Okay, so we'll see how to compute its value. Do you know what's the formulation of expectation? Formula of expectation is this. So if you have e of x, expectation of x, and then you write summation of, let's suppose k goes from 0 to infinity, and you will say k multiplied by PMF, probability. This is the definition. This is by definition of expectation. This is by definition. And then if you have to evaluate this thing for, let's suppose, the geometric variable that we are taking into consideration, we'll write the PMF of that. So e of x, this is equal to summation of k is from 0, let's suppose, infinity, and then we'll say k into 1 minus probability, that is the probability of failure. So we'll take this k multiplied by p. We'll use the definition that we earlier discussed. So if you see Ross and Children will use this definition. It doesn't make much of a difference. You just have to adjust the value. Now in order to compute this PMF, so what you can do is I can just write q. Let's suppose I'll make the equation simplistic. K is equal 0. Keep an eye on my calculations because I have a tendency to write here and there, so you have to keep in check. K, I'll write q of k probability. So now what I can do is I could have done one thing if this k was not here, and one more thing that you can do over here is, in this case, let's suppose, in order to see if these things are actual PMF. So PMF has the property that each value in that PMF, if we take just one point and compute the probability of that, it should be non-negative, and once you sum that up, it should be summing up to 1. So if I just write it roughly over here, so you know PMF is this. PMF is p x takes value k. This is equal to 1 minus p to the power k. So now if I have to check if it is a valid PMF, how can I check it's a valid PMF? So you have to compute that it is non-zero, that is probability. If I take any instance, or if I take any random value of a random variable and I check what is the probability of that, it should be non-negative. And the second thing is, if I sum it or up on the whole of this value, so it should be 1. So here I can do something of this sort. I can say if I sum this up, if I k for let's suppose k goes from 0 to, let's suppose, n. So what I can do is I can say qk. I'll say k goes from, say. So now if you see this p does not depend on k, so I can bring this out. So I can say k goes from 0 to. So this over here is a geometric series. This over here is a geometric series. Here, say the sum of geometric series is this. So you can quote me on this anywhere, and you can prove this. So the sum of this is 1 divided by 1 minus. If you see this term, okay, this is a geometric series. The sum of geometric series is 1 divided by 1 minus whatever there. I can write it p divided by 1. You know 1 minus q is equal to p, so this is equal to 1. And I sum over all of these things, so I got this to be 1. This is a valid PMF. So for validity of PMF, what you have to check is, you have to check that it should be non-negative. That we clearly know that this is non-negative because p is non-negative. Okay, when p is non-negative, so this will either be 0 or greater than 0. And similarly, if I have to check that this p, the sum of all these values which a random variable can take should be equal to 1, so I sum it up. So I took this p out, and then I said this is a geometric progression. The sum of geometric progression over here is 1 minus q. So over here you can see that I know this. Why I just showed you this? Because here if you see this k is somehow bugging me up. So if I did not have this k, the rest I had this, this and this, I could have taken p out, and I could have written the other thing as sum of geometric progression, and I could have that formula in order to remove this k. So we'll use a bit of calculus. So probably that much you will know. So we'll pause over here and we'll come back to this point again. So before that, we'll try to solve this. So over here I know. So what I can do is I can say, let's suppose I have this q of k, summation of say k goes from 0 to, and I know the geometric sum is 1 divided by 1 minus q. This is what I know. Okay, from there I showed you. So I want to get this into this format. So how I can do is I can differentiate on both the sides. Yeah, I can differentiate on both sides. Once I differentiate, if I have x to the power n, so if I differentiate this, take this as an assumption for now. So once we go to calculus, you will see that we'll prove this formula. So if we differentiate this, so you get this as n x n minus. Here I know this much. Once you differentiate, if I differentiate this, dash of x is, so accordingly I'll differentiate this. So I'll say d by dq of summation of k is equal to 0 by q of 1 minus. So I'll differentiate it because I want this. I want it to be in this format. I took this qk and I want this k to be in the front. That's why I differentiated. I'm also giving you the rationale while proving these things. That's what makes mathematics special. So let's suppose if I told you all of this thing in words, I could have not manipulated all of these stuff. Okay, because it will look so verbose in if I say these in words. So I would have no clue how to manipulate it, how to perform algebra on it. Now because I have introduced symbols and these things, I at least have an idea how to manipulate it, how to perform algebra, because I wanted to get this in this fashion, k cube, because I know this k I can bring it down by using differentiation. So if I now differentiate this, so you'll see this differentiation is equal, let's suppose, so I'll say summation of k goes from 0 to infinity, and then this k to k minus 1. Okay, so because of this I introduced one more problem. The problem is now here I have k minus 1, and we'll take care of this also. So if I differentiate this, so this will be 1 divided by 1 minus. So here I am putting maybe a red dot. Why? Because I haven't taught you differentiation. So here I am assuming that this step you will know, and this still is debt on me. So once we go to calculus, you people should derive it from first principle without using the formulation that d by dx of xn is n x n minus something of this sort. So this is a debt on me. I'm putting a red dot over here. Okay, so now again I want to have this k q k. So I'll bring one q out of this. What I can write is I'll say q, and I'll say summation of k is equal to 0 to infinity k. I'll multiply, basically I'll rather multiply. I'll also multiply. I'll multiply so that this becomes multiplied by q, so this becomes q raised to power k. So now I got this into this format. Now this is what I want. Q divided by 1 minus q. Now I can substitute it over there. I can, once I substitute this, I can say expectation of x. So I'll take this. Okay, so I'm taking expectation of x is equal to summation of k q. We have k. No. Now I know the value of this. I know value of this portion. Value of this portion. This is equal to q divided by 1 minus multiply this q multiply. Here 1 minus q is also p. This is p square by. So the expectation of x is. Any questions on this calculation? Okay, the first thing is you should reason it. So why am I also showing you the proofs? Because I also want to show you that the power of mathematics. The power of mathematics lies in the abstraction. Because let's suppose if you take number 1, if I say number 1, number 2, these are not physical entities. Okay, these are just abstraction of some concepts. If I say one person, two people, or something of that sort, if I say two bottles, two pens, so pen is a physical entity, but two is a concept that is defined on the pen. Okay, there can be two pens, there can be two bottles, there can be two mobile phones, there can be two laptops. Two is an abstraction, but a physical entity that is corresponding to it might be some physical material thing which will exist in the physical world. So here similarly, when I told you that what is the expectation of this, so the thing we could have done is we could have written in verbosity, okay, what can I expect from this? Then in order to perform algebra on it, it would have been very tedious and very difficult to perform algebra on that. So once we brought in these symbols, so we did some tinkering over here and there, we performed some algebra, and sometimes it does not make sense also. Why is it giving this way? But mathematics has certain rules. So algebra has rules. By the help of those rules, I derived this result. So the expectation is q divided by p. The q basically means failure divided by the success. This is my expect. This is what I can expect in a geometric random variable. Now, in order to, let's suppose, also derive the formulation for this, if you have to derive formulation for this, you only have to do one thing. You have to use linearity of expectation, because you will say that expectation, and then you will probably just subtract 1. So in here you are adding 1. In this you are adding 1. So in the original formulation, so in this formulation, because you had k over here, and in here you had k minus 1, you have to subtract 1 in this formulation. If you see, the expectation of x is equal to q by p. But this is the case when we took when we took that k basically means the number of failures. So if you take the Ross and Sheldon formulation, you don't have to derive the whole formula again. You only have to do expectation of x is q by p minus 1, because you just overcounted one thing in the original definition. So if you do this, you will come to, this is 1 minus p divided by minus 1. So this is 1 by p probably. So you'll see both these formulations being. So expectation of x is equal to q by p. So you now know why is it q by p, because here we are taking k. In the other case, you are taking k minus 1. Expectation of x is, you will see both of these expectations being written. I explicitly told you that in the first formulation, we consider that x is a random variable which considers number of failures. Okay? So in here we consider number of failures until that success occurred. Okay? Here we see number of failures. So there are two interpretations of this, and you can see there is a change in formulation. But if you derive one thing, you just have to adjust the other formulation. Any questions till here? Any questions on geometry? So what I said is, in the books you can see this geometric random variable defined two ways. Sometimes people are saying number of failures before first success. Okay, you are just computing the failures, and sometimes you will see number of tosses till you see the first success. So you'll count the number of tosses, and you will count number of trials, rather, not tosses, number of trials. Okay, in this I give an example. Let's suppose you have a coin, and let's say coin toss head is called as success and tail is called as failure. So let's say you have this, you have tail, head, so you got success on the fourth toss. So in the second case, trials till you get the first success. So the value for this will be 4, okay, because it took you 4 trials to get you to the success. So in this case, when you say failure before the first success, that means it will take you only 3 failures. So there are 3 failures till the first success. So you see there is a off by 1 error. Basically, some people overcount by 1, or some people don't count that one. So we went with this formulation where we have this 4. We took this k also. So we said 1 minus p to the power k. It took us k tosses to reach these failures, and then we said multiplied by last p. This is the success, and this is, so that's why you see the 2 formulations. So once I compute the formulation for this 1 minus p to the power k, so I just, because expectation is linear, so I just subtracted minus 1 from it. So for p is equal to, for this k, you got this q by, because you know this is 1 minus p or k multiplied by p, and summation whatever, and then for this formulation, because we have 1 minus p, k minus 1 divided by p, k summation equals 0 to infinity. So we got the formulation. Here it is. The trick that we used over here, I wanted to also show you that, because once you see mathematics, so you have to somehow evaluate. You have to get the value of this. So what I said is, I said q k, I know it, okay, with the summation, and I know how to get this k also. If I differentiate it, so I'll get this, because I knew this qk is equal to 1 by 1 minus q. So this is sum of geometric progression over there. So I differentiated it, and because the differentiation I got this, but I wanted to get rid of this k minus 1. So what I did is I multiplied both sides by q. So that's why I got a q on this side. I got multiplied q on this side so that I can remove this 1 from here, and now I perfectly have this summation of k goes from 0 to infinity k 2 to the power k is equal to this. So I substituted this value instead of this, and once I have that, then I did some again algebra and I landed at the formulation. Once I want the formulation for the other case, I just subtracted 1 because of the linearity of x. Write this also. This is because of linearity of x. Then I read. Yes, go ahead, please. Okay, so here there was a mistake, minor mistake. So we're using this linearity of expectation wrong. So it should have not been a q by p minus 1 or q1 minus q by p. So it should have been 1 plus. It should have been 1 plus q divided by p. So once you substitute these values now, okay, because in the first case you are counting k, and here you are counting one extra. So in this case, what you can do is once you added this one, so you'll get p plus q divided by p. This is plus 1 minus p divided by, so you'll get 1. And one more way of proving it, because we have the PMF given, so expectation of x is equal to summation of k goes from 0 to infinity. This is k 1 minus p k minus 1 p. You take this q to, so here we can say the summation of k is equal to 0 infinity k 1 minus 2 to the power k, and then we can directly use the result that we got from the calculus, that is this result over here, without multiplying this q on the both sides. So we'll get 1 divided by 1 minus q. So I can substitute 1 divided by 1 minus q divided by multiplied. This is p divided by. You can do it in both the ways. So you can use linearity or you can use the definition. Okay, I think you people were correct that I was using it wrong over here. So I was doing q minus p minus 1. So but it should have been other way around. I have added. So this is expectation. So what we saw in geometric random variable, so we computed its PMF, we computed its expectation, and PMF also depends on how do you define this. The expectation is either q by p or 1 by p. So when you are solving the problem, is do take care how are you defining the random variable. PMF is equal to 1 minus p k q, or equal to 1 minus k minus 1. Okay, let's do a question to clarify this. So you can use any of the definitions, and then you have to tell me which definition you use. But it's good that you're paying attention. Let's go to the question. Okay, the question goes like this. So let's suppose there's an urn. The urn contains n white balls and m black balls. There are n white balls and there are m black balls. The balls are randomly selected one at a time. So we have randomly selecting a ball and one at a time until one black ball is obtained. Until one black ball is obtained. So here again, if you see, until one black ball is obtained, that means getting a black ball is a success. Okay, this is question. So we have an urn in which we have n white balls and m black balls. So we keep on sampling the balls until one black ball is obtained. If we assume that each ball selected is replaced, so we are replacing it. It is with replacement. So you are just putting the ball back in there. You are just driving the ball, and if it's, let's suppose, white ball, you are putting it back. So again, you are drawing the ball. If it is a white ball, you are again putting it back till you find a black ball. So once you find a black ball, that means you are getting a success. So if we assume that each ball selected is replaced before the next one is drawn, what is the probability? Exactly n draws are needed. So a question is exactly n draws are needed, and part B of this question is at least k draws are needed. You clearly see that this is a geometric process, okay? Because here, once you are drawing the ball, so you will stop until you will get a success. So here you will only stop if you get one black ball, because black ball here is considered a success. Okay, and balls are also drawn with replacement. Now the question is that you have to compute what is the probability that exactly n draws are needed till we get the first black ball, or at least k draws are needed. So I'll pause here for at least a couple of minutes to give you time to solve this question, please. Now, in order to solve this question, we have to find failure and success probability. So failure over here is getting a white ball. Getting a white ball is a failure. Okay, and success over here is getting a black ball. A black ball. If you use naive definition of probabilities, that says that that each of these balls are equally likely. So you have m plus n balls in the urn. So whenever you draw a ball, each of the balls is equally likely. So I can say what is the failure probability then? The failure probability is, let's suppose I have n of these white balls. In total, I have m plus n balls. So this is failure probability because these are my total cases. These are my favorable cases. Success probability is m divided by m plus n. The first question was asking us, what is the probability that exactly n draws are needed? That means you should have failure, failure, failure. At the end, you should have success. So all of these till n minus 1, till n minus 1, you should have failures, and at the end, you should have a success. Okay, now I know the failure probability. So what is the failure probability? Failure probability is this. Failure probability over here is n divided by m plus n to the power n minus 1. Okay, this is my failure probability. And then at the end, last is m divided by m. So this is the answer to part A. Yes, questions. So I hope that you got this answer for part A. Now part B says that you exactly should have k successes. Okay, at least I think at least k successes. So in the first you have exactly n draws. So now at least k successes. So that means you have to compute probability of x takes value greater or equal to k. Okay, so let's suppose what the meaning of this is, if I take n trials, let's suppose I have n trials. In the n trials, last will be success because I'll stop once I get success. Okay, now I'm left with n minus 1 trials. So in this n minus 1, I should at least have k failures or k plus 1, k plus 2, whatever. So what I'm saying is failure probability is n divided by m plus n. This is my failure probability. Okay. So till here I should fail, but this n should start from k. I'm saying that n should start from k to let's suppose go all the way, go till infinity, or all the failures, and then multiplied by, because at the end I should get last one success. I'll get m divided by. This is the answer for part number. Okay, so after this question, so as I said that expectation of x is equal to q by p when we took that k, and when we took that additional one, so expectation of x was 1 by p. So I saw an elegant proof by using the recursive equation. So the proof goes like this. So let's consider that we have the c. Let's suppose c is the expectation. Okay? So if you see this c is an expectation. So let's suppose you got failure. Let's suppose in the first process. So what you will write is, you will say 0. Let's suppose probability of this is q, something of this sort, and then again you will repeat the process. Now you'll say the first time plus again the process will repeat. You will start with c because each of the trial is independent. Let's suppose you started with c. C is the expectation. So you said, okay, I got failure. Now let's suppose I'll start with the first, and again the problem will repeat. I'll see 1 plus c of this. So this is 0 multiplied by q plus. Now I'll get let's suppose some success. I'll get q into 1 plus c, something of this sort. So this is a recursive equation. I first need to check it. So this is c is equal q plus cq. This is 1 minus q divided by, yeah, this is right. So here, so if you see success probability over here, let's suppose success probability is p. So you had success probability. I'll explain you this solution. So this is called as recursive. This was a damn good solution when I. Okay, so here the probability of success is p. Okay, and the probability of failure obviously is q. So now let's suppose you have 0 failure. So what you can say is, you can see like something of this sort. So x is equal 0 is a failure. So you can also see it like this. X is equal 1 plus x dash, where x dash is the geometric random variable. So again you see c, and then you are seeing that probability of success. Let's suppose you got 0 multiplied by probability of success, and on the initial track, let's suppose you failed. So here this is 0 multiplied by p. So because success probability was p, so on the initial go you failed, so 0 multiplied by p. Again the problem is reduced now because the first trial is done. Now in the second trial the same problem occurs, so you have to repeat this problem. You have to repeat this recursive solution. You're again getting C, and then you're multiplying it with the Q, because Q is the failure probability, because you got 0 multiplied by P plus 1 plus Q, and when I just evaluate it recursively, so I got it like this. So I'll say C is equal Q plus CQ, and I took this C over here, so I got 1 minus Q into C minus CQ, this is equal to Q, equal to I took this over here, so I took C common out of this, so this is 1 minus Q, this is equal to and I took the C over here and then took the denominator. This was a pretty good, I think pretty good solution given as a recursive. So this also matched the calculus problem, confirm the calculus. So here what we did is, so this is actually called memoryless property. Here we'll see also this. So I'll give you questions in assignment. So this over here is called as memoryless property. So why is it called memoryless property? Because you resort to the same problem. So once you failed, it again starts from the same thing. Okay, let's suppose you got failure in the first run. Once you got failure, okay, then from the second problem you got one failure. Now again the problem starts from the failure. Okay, so if you truncate it down, if you have something of this sort, fail, still had. So let's suppose if you got failed the first time, similarly the problem boils down to the same thing. That's why we again brought down the recursive equation, this C back. So once you fail, this is probability of success multiplied by 0, because you failed the first try, and plus then this 1 plus C. Okay, because the problem again repeated itself, so that's why we came up with this C, because now this is C multiplied with the failure. So once we evaluate this, so this C is equal to Q divided by 1 minus Q, and we got the same solution. So as I said, this is called as memoryless property. I'll give you assignment problems on this memoryless property, so that once you see such questions, you assume something. Let's suppose expectation is C. Okay, once the first time it's a failure, again the question remains the same. So C plus this, so you will evaluate many of these things like this. So this is the expectation, how we can compute expectation. There are a lot of problems that we can do in this geometric random variable, but we'll probably do it in the assignments, or maybe in the project somewhere we'll use this. Okay, let's now go to the next distribution. So far what we have seen is just a couple revision. So we have seen Bernoulli random variable, we have seen binomial random variable, we have seen hypergeometric, we have now seen geometric. Okay, why am I teaching you all this? Because a lot of phenomenon will follow these random variables. Okay, I will at least go through 11 to 12 distributions, 11 to 12 random variables, including discrete and including continuous random variables, and you will see that probably 90% of the cases that you will encounter either in real life or in deep learning or machine learning will follow one of these distributions. And we have now well studied distribution. You at least know PMF. Now you know expectation. We'll also go to the variance concept, while you will compute the variance. So once you see any phenomenon related with that, then you will have a clear idea. As I said, if any person has to learn only one subject in mathematics to be smarter than usual average person, so he should study probability and statistics. Because why probability? Probability gives you a framework to deal with uncertainty. Okay, and the whole life is uncertain. Our whole life is uncertain. There is almost no certainty in all the cases that we encounter in life. So only one subject that you should master is probability and stats. And you know, in the probability and stats, there is the margin of error also. So it's not that you have to come with a ballpark number. So if you come at around that number, so still you will take better decisions, you'll take informed decisions than other people. Okay, so that's how this important, how important this field is. People were doing this analysis before even they named it as machine learning. They were naming it as pattern recognition, statistical analysis. Then once the advent of computers, we named it as machine learning and deep learning, because what we are doing is just function approximations by using all these parameters. So in Bernoulli, you have this parameter probability of success. In binomial, you have two parameters, n and p. In hypergeometric, you had these two bins, if you know that, tagged and not tagged. So in geometric, now you again had this till the last success is seen. You're given the probability of success. And now let's see what's called as negative binomial random variable. This is called as negative random binomial. This is the distribution's name. Negative binomial is again a discrete. We're still studying the discrete random variables. So in this, it models number of failures. It models number of failures in a sequence of independent Bernoulli trials. Now if you see, this is what I can say, this is generalization of geometric generalization of geometric random variable. So here in geometric random variable, what we are seeing is that, so we will number of failures till we get the first success, or number of, let's suppose all these flips till we get the first success, something of that sort. So in this case, what we are trying to do is we are saying how many, so let's suppose if we consider r, so here you will see this as written like this, let's suppose negative binomial random variable, something of this sort. So there will be r and a number and a p, these are two parameters. So r here is number of successes we want to achieve, this is number of successes we want to achieve. Okay, and each of the trial you will see in geometric you just want to achieve one success. You are saying that count all the failures till I get the success, so you call that a geometric random variable. But in this case, what you are saying is I want r number of successes. Okay, I want r number of successes irrespective of how many failures I get, and then you say number of failures till I get r successes. Okay, that as I said, this is some sort of generalization of geometric random. In geometric random variable, we are just saying that if I get one success, I'm done. And then basically you are computing number of failures till I get one success. So in this case, you are saying that I am interested in r successes, and then I will see number of failures till I get the r successes. Is the definition clear, by the way? For how many of you people is this clear? And for how many of you agree on this? There is a generalization of geometric random variable. So now we have defined this negative binomial process. As I said, this is the generalization of geometric random variable. The first thing that should come to your mind, okay, if I want r successes, in n trials, so I'll say, let's suppose I have n trials. So for sure, the last trial will be a success. It's a short, because that is why I stopped. I wanted r successes, so I got r success. So this is my r success. Okay, so before this, I am now left with n minus 1 trials. There are multiple ways of thinking at it. If I have to compute PMF, I can say, what is the probability of getting r successes? I can compute that probability of getting r successes, or I can define a random variable x, which is number of failures till I get r success, number of failures before r successes. This is one way. Or I can just define PM. I can say probability of r success. Okay, because as I said, so I have these n trials. Let's consider I have performed n trial, and I have stopped in the nth trial because the nth trial was a short success. That is why I stopped, because it was my rth success. So now what I have to do is I can break this down problem into two steps. I can say now the last is my rth success. So I got rth success, that is I got a success p. So I'll just write it separately. Now before this, I should have got r minus 1 success. Okay, so out of how many things? So I should get r minus 1 success out of n minus 1, because at the nth trial I got a success. Okay, this is basically filling the places. So I had to fill, let's suppose I had the success in this, I have to choose r minus 1 place for the success to fill. So how many ways to fill that? So that is n minus 1, choose r minus 1. You have to choose, and out of n minus 1 place, you have to choose r minus 1 place. That's why I can choose in this way. Now r success is this. So what is the probability? This is success r minus 1, because I got successful r minus 1 time. Failure q, basically you got the failure n minus, so n minus 1 minus r minus 1. This is n minus 1 minus r minus 1. This is plus 1. So you got n minus r. Right? So this is probability of r success. So I can again write it down, simplify it a bit. This is n minus 1, r minus 1, probability of r q. This is probability of r success. This is, if I write it in terms of random variable, so I said x is the number of failures before. So I can write x can take value x. Basically, I should get x failures before I get r success. X failures basically means I should get q to the power x, these many number of failures. How many successes then? R successes. I should get r success. This is p to the power r. And now I have just filled these values. So that value came out to be r minus. That value came out to be I have to get r minus 1 out of how many? X minus r minus 1, that is x plus r minus x is number of failures. This is the probability. I want x failures, so I got x failures. Okay, so again think it in these terms. So think in these terms, because rth was my success. So before I had n-1 trials. So in that I said you have to get r-1 because you have failures for x. So there were failures x. Now whatever is left is x. You have to add this r+1 in that, and you have to choose from there r-1. So you got p or r and q x, y. And I said if you have to compute this, you just have to see this n-r equal to x. Just put the value in, you will get it back like this. Okay, so this over here is called as, this is our PMF of negative binomial distribution. So again, word of caution that you don't have to memorize these formulas. Don't memorize them. Just try to see how can you model the process, and how can you at least learn to model this, because it's not the way. The way is not to just memorize the formulas, because sometimes you'll have to come up with your own distribution. You'll have to learn modeling. So you have to learn modeling of the phenomenon. Learn modeling. Not learn modeling, you have to ramp walk, but rather you have to learn modeling of the real world phenomenon probabilistically, so that you can apply probability, a framework of probability onto this. Okay, now I'll just give you a question. Suppose you are running a quality test on batteries. You are running a quality test on batteries, and each battery has 70% chance of working. That is success probability. Success probability is 0.7. So you want to find the probability that you observe 3 failures. You observe 3 failures before observing 5 working batteries. Before observing 5 working batteries. So what's the probability of this? You want to find that the probability that you observe 3 failures before observing 5 working batteries. So what is the probability of this? You want to see 3 failures before you see 5 batteries working. I'll give you maybe a minute or so to think about it. Again, if you see this is a negative binomial problem, you can directly use formula, or you can just sort of think from first principles to use this formula, to just make this map into your head and then use the formula. Some people directly will jump on the formula at this point, but I want you people to reason from the first principles. Make, okay, I want 3 failures, and so that I observe this 5 working batteries. So what's the probability? Okay, now the probability we have to find is that we have to get 3 failures before till we observe the 5 working batteries. So what I'm saying is, so at the end we'll have 1 working battery. So now we are left with only 7 trials. In total we had 8 trials. So now out of these 8 trials, in the 7 trials we should get the failures. So we should get 3 failures in these 7 trials. There are a lot more methods than the way you can do it. So what I can do is, I know that the probability of success is 0.7. So I want to get successful 5 times, and I want failure to be 0.3 times. Now I just have to permute this. So I have to take 3 positions out of the 7. Okay, this is the answer. Okay, so I said some other people would have just used the formula. They would have said x is equal to 3 over here. So success is basically over here, r is equal to 5. So they would have just resort to this formula. Probability x is equal to 3 is x plus r minus 1. So that is 3 plus 5 minus 1 divided by 5, combination 5 minus 1. And then 0.7 to the power, because r is 5, success is 5. And then we have to 0.3 to the power x, that is 3. So they would again came to this. As I said, you could have derived it from the first principle. So one more method would have been, just take this final as working battery and then just permute it. That's what we did over here. I hope that you at least got some understanding of these things, how to think about this. So this was negative binomial random distribution. So can you now compute the expectation of it? So again, you have to compute expectation of this. You have to compute expectation of, because we're getting too late, so we'll stop this session on this expectation. So I hope you will work on this expectation. So this is your homework. So we are left with a couple of distributions, couple of more distributions. So we're left with a couple of concepts that I'll name. So Poisson's distribution, very important distribution, one of the most important distribution, and one of the used distribution in real world. That's why I kept it at the end, because I don't want to rush to it. I wanted to solve a lot of problems. So we'll solve a lot of examples, because now if you at least have got the theory notations, so we'll solve examples based on what we have seen. Then we'll go to this Poisson's distribution, and then we'll see variance also. Variances and the concept, and on the expectations, we'll not on the expectation. There is a full-fledged discussion that we probably might have in couple of sessions. So we'll take couple of sessions to just understand expectation because we have a lot of algorithms, expectation maximizing algorithm. So we want to maximize expectation in machine learning a lot of times. So that's why we will have on this variance and expectation, we'll have a much detailed discussion. How are they used in machine learning? How are they used in deep learning? Okay, so in the next section we'll take examples, and then we'll see a couple of more distributions. We'll see Poisson's distribution, and I hope you will compute the expectation of this negative binomial distribution, and you have to compute expectation of hypergeometric distribution. This is the homework for you, hypergeometric distribution. And one more thing I wanted to see is I wanted to show you, I wanted to prove linearity of expectation. Linearity of expectation. You also try this up. So this again is a homework. 3 things that we have to do: compute expectation of hypergeometric and negative binomial distribution, and prove linearity of expectation. So these are 3 homeworks, and if you people are doing it, then we'll just summarize,
discussing random
5-6 minute discussion on
random
these things, just derive it. Otherwise, if you had problems with deriving these, so it will take probably 10-20 minutes to derive these in the section. So from next section we'll do examples, then Poisson distribution, and then variance, and probably we'll close the discrete random variable, and we'll move back to calculus. Not back to, we'll start calculus.
Also saw what is negative binomial. Negative binomial random. As I said that all of these variables probably will see maybe 10, 12, 13 different types of these random variables, and they'll describe some phenomenon, they'll describe some real world process. And once we have good understanding of these things, maybe 90% of the things that we'll do in machine learning, deep learning, they'll probably follow one of the process. And having the notion that you have learned these random variables, you should be able to come with your own random variables. If you see a pattern somewhere, so you just need to sort of abstract the details, and what I can say is mathematicize it, if that is the word. So you sort of use mathematics to sort of abstract all the details and forget about what's the actual process, and see a pattern and come up with the random variable of your own. So these random variables are standard random variable defined. So probably you won't be needing that you will have to define your own random variable. But I hope that you will have developed a notion, you would have at least developed such a sense that you can come up with your own random variable. So these are the random variables that we discussed so far, and I'll ask one of you maybe summarize it in a couple of words, and I'll pause the recording over here. So let's have a short summary on this. So what is a Bernoulli random variable? So in Bernoulli random variable, a process can be either having the output as success or failure. So let's suppose in terms of coin toss, you can have either head or you can have tail. So this is success or this is a failure, and it has some probability of it, that is P probability of success. So any phenomenon of this thing can be modeled as a Bernoulli random variable. Then we said what is binomial. So binomial, basically if you keep on performing these Bernoulli random trials independently, so we'll call this as a binomial process. So binomial n comma p, that is you have n trials and each has success probability of p. So you keep on doing this Bernoulli trials. So what is hypergeometric? So in hypergeometric, as Fahad mentioned, that here in binomial we take these trials independently, but here the trials may be dependent, because of, as a consequence of this, that p might get changed. Okay, so that's what makes it hypergeometric. So if you remember the example, so you have some things of 2, you have r plus b balls, and you want to sample n balls. Out of these n balls, now you are thinking, what is the probability that I'll have k red balls out of these n balls? Okay, you are sampling n balls out of this, and out of this n, I want k balls to be red, k red balls. So this is one example of hypergeometric. Then we have geometric. So what is geometric? In geometric, we'll keep on performing trials till we get the first success. So this is number of failures till we get the first success. This is how it is defined, geometric random variable. As I said, there is a catch. Some people say number of failures till we get the first success, or they say number of trials till we get first success. So let's suppose some people count from 0, some people also count from 1. So where does this come from? Let's say we take example of head and tail. So if we consider head as to be success, so if somebody got head on the first trial, that means he or she got success on the first trial. So here some people will say that there are 0 failures before the first success. But some people say that it requires at least 1 toss. So depending on how you define these things, formulation accordingly change, and it's not a big deal to change the formulations. You can just perform basic algebra to come up with the formulation. And then what is negative binomial? So in negative binomial, what you basically do is, so you are having this as a generalization of geometry. Now you don't just want 1 success, you want r successes. You are saying that how many number of failures are there till I get r success. So this again can be dependent. Will you start from 0 or will you start from 1? So this is just generic way of saying geometric. If let's suppose you have only r is equal to 1, that is number of success is 1, that it becomes geometric random variable, because you are saying that I just want 1 success and I want to count number of failures before that, or I want to compute number of trials before that. Similarly, if you have now r is equal to 2, 3, it is a generic geometric variable, random variable. That means it is negative binomial random. So if you see the formulation of this negative random binomial variable, so negative binomial random variable. If I say x is sampled from this, so if I show you the formulation was something of this sort. You have n minus 1 color, you have n minus 1 r minus 1 e to the power r 1 minus power n minus. So this was the formula. So this is actually negative binomial, called as negative binomial coefficient. So if you see binomial theorem, that is x plus y to the power n, you can expand it, ncr, x raised for this, y raised for this. But if you have something of this sort, x plus y to the power, let's suppose minus n, you can also expand this. So this somehow comes out to be of a form like this. So that's why it's called negative binomial random variable. So if you see, why was this called as binomial random variable? Because somehow it was similarly looking to this formulation. When you have this binomial, you can expand it by binomial theorem. The coefficients you will get were similar to this. So why is this called as negative binomial? It has nothing to do otherwise with negation or something. This was named because it is an expansion of this term. So if you expand this, so you will get term like this. You will get terms like this. That's why it's called as negative binomial random variable. Let's do some question on this, and I'll put the question over here, then give you maybe a few minutes to think over it and come with a solution. The question goes like this. I'll just give you the prior that the question will be on negative binomial random variable, because we have done enough questions on Bernoulli, binomial, geometric, and then we'll do some questions on geometric and negative binomial, and then we'll also do some questions on expectation, and then we'll move to the last distribution, that is Poisson distribution. The problem goes like this. So we have a mathematician who smokes cigarettes maybe. Mathematician is there, so who smokes cigarettes. So now this mathematician, he carries two matchboxes, because he has to light up the cigarette or a pipe. So at all times this mathematician carries two matchboxes. So one is in his left pocket and one in his right pocket. So one in left pocket and one in right pocket. Okay. So each time he needs a match, he is equally likely to take it from either pocket. So this is given. So whenever he needs a match, so if he needs to like suppose burn the pipe, so what he has to do is he'll take the match from either pockets with equal probability. Consider the moment when the mathematician first discovers that one of his matchboxes is empty. If it is assumed that both matchboxes initially contain n matches, so initially we have n matches and matchsticks, basically match. What is the probability that there are exactly k matches in the other box? What is the probability? What is probability that there are exactly k matches in the other box? Again, repeating the question. The question goes like this. At all times, a pipe smoking mathematician carries two matchboxes, one in his left pocket and one in his right pocket. So each time he needs a match, he is equally likely to take it from either pocket. Consider the moment when mathematician first discovers that one of his matchboxes is empty. If it is assumed that the matchbox initially contains n matches, what is the probability that there are exactly k matches in the other box? This is the question. You have to compute this probability. So once he discovers that the box is empty now, so what is the probability the other box will have exactly k matches? Okay, now if you see the question here asks us, so what is the probability that there are exactly k matches in other box? So assuming that one box got empty. So how will one box get empty? So we have these two boxes. This is, let's say, box 1 or box 2. We'll demarcate it, or either by box 1 left or box right. So now here we have one box. Let's suppose we'll consider this left box. So let's suppose we'll empty this box out. So if we empty this box out, so that means picking a match from this box is a success. So picking a match from box L is success. Why? Because I said I'll empty the left box first. Now emptying the box basically means success. If I am taking match out of that box, that means this is successful event. Then what I'll do is, because I'll have to empty this out, so how many successes do I want? Then I actually want n successes. But at n plus 1, I'll realize that this matchbox has this is emptied out. So I basically have n plus 1 times I'll have to pick up the match from this box so as to empty it out. Okay, so this will ensure me. So n trials will ensure that I'll take each and every match in here, because we have n matches in both the boxes initially. N match, if I take n match from this left box, so it will ensure that I have taken each and every match from this box, and on the n plus 1th trial, so I'll now get to know that this match box is empty, okay, on this n plus 1 trials. So now how many matches do I want to be in the other box? So other box is, let's suppose, this right box. So now question says me, what is the probability that there are exactly k matches? So now here it should be only k match should be left. So how will the k match be left? So if I have taken n minus k out of this, so if I have taken out n minus k match from this, then only there will be k match left. So here this is success and this is failure. It's a typical problem of negative binomial random variable. Why? Because here we want these many successes, okay, till we'll stop. Okay, so we have to count number of failures. So basically number of failures till we stop over here. So we'll stop at the last thing. Okay? Now we have in total the trials. Total number of trials that we are performing is n plus 1 plus n minus k. This is the total number of trials we are performing. This is 2n minus k plus 1. These many trials we are performing on this. Now in these number of trials, what we want success and failure. So how many successes do we want? We want n plus 1 success and these many failures. Okay. Now we can model this problem like this. Again, negative binomial random variables. So consider it a sequence like this: failure, success, success, failure, and so on. Till last, I will have to get success. Then I'll stop. And before this, I'll have to get n successes. So n successes I'll get before, because I want n plus 1 success, and I'll only stop if I got n plus 1 success. That is, when I check the match on the left hand side, let's suppose it's empty. So I'll stop over here. So now the question becomes like this. So success probability, I'll have p to the power number of trials I performed there. Okay, number of successes, basically number of successes will be n plus 1. I can directly raise it to the power n plus 1, and q to the power. Okay, and number of failures I want over here. So this is n minus k. Okay, now I just have to reduce the problem into combination. So now I have these many left. I have n minus 1 places left. So this is total number of trials. So trials are there. So how many trials are there? If total trials were 2n minus k plus 1. So how many trials are left now? Because last is short success. So then we are left with 2n minus k trials. Out of these things, we have to choose n successes. Okay, and success probability is p is this, q is this. Now p and q is equal. We know that this is equal. So we can write 2n minus k divided by n, not choose n, 0.5 to the power 2n minus k plus 1. Okay, this is the probability of that event. Now you know that each of these is equally likely, so you can write 2 to the power p of e is this. Okay, if we consider that e denotes the event that mathematician discovers that, let's suppose, match box is empty, so we can say 2 to the power 2 multiplied by this, because both of these are equally likely. So this is the. Okay, so now as I said, you can also directly use the formulation. So the formula of negative random variable was n minus 1 r minus 1 p to the power n minus 1, and I think q to the power r minus 1 of this sort. If you see, so this is the form n minus r. So p to the power r n minus p to the power r. Okay, again you can clearly see I myself don't remember the formula, so it is not a big case that you can directly derive them on the fly. So you just have to now check what is the value of n, what is r, and what is p here. So these three values if you got, you can directly substitute it. So n over here, if I directly say this is 2n minus k plus 1, and r value of r here equal to n plus 1. So this is the number of successes, and we have this 1 by 2. So if I substitute this, you will exactly get this answer. If I substitute this, and you will just have to perform some algebra. Any doubts on this question? So this question is on expectations. And the problem goes like this. This was tagged as one of the hardest problem which came on that particular exam. The problem goes like this. It says you are given a random permutation. So you are given a random permutation of 1 to n numbers. So numbers are like this: 1, 2, 5, 3, something of this sort. So you are given n numbers, n distinct numbers, or whatever it is. So you are given a random permutation of integers from 1 to n. That is random in arrangement, as I said. So now I'll define something which is called as local maxima. So what is the local maxima? So if I write something of this sort, 3, 4, 5, 2, 1, 4, 9, something of this sort. So if I take a number, like let's suppose I'll take number this, or I'll take number 5, let's say I'll take this 5 number. So this will be considered local maxima if the number on the left is less than and number on the right is also less than. It's strictly less than. It should not be equal. So both of the numbers should be less than. Okay. So 4 and 2 should be less than 5. I'll call this 5 as local maxima. Similarly, I'll call this 9 as local maxima. It's a number which is at end. I'll call it local maxima if it is greater than the number which is on the left side of it. So on the starting number, if a number is let's suppose I'll make this number a little bigger. Let's suppose I'll write 7 over here, so I'll also make it local maximum. So this thing is local maximum because the number on the right side of this is smaller than it. So I hope that you got the concept local maximum. The question was, you are given a random permutation of integers from numbers 1 to n. Okay, a local maxima is this how it is defined. So now you have to compute what is the expected number of local maxima. Expected number of expected number of local maximas. So this is the question. You have to compute expectations somehow. The question is that you have to find expected number of local maxima. So okay, let's take any sequence. If I take a sequence 5, 4, 9, 2, 1, 8, something of this sort. Now if I can see it over here, I'll have two types of numbers. I'll have numbers which are extremes, that means this number and this number, this 5 and 8. I'll have numbers which are in the middle. Now I'll have to compute two things. I'll have to compute probability that extreme numbers are local maxima. How I can compute that? So if I take this example 5 and 4, so there are only two possibilities. It can be 5 4 or 4 5. So for this number to be local maxima, it is 1 by 2. Okay, because it can be 5 4 or 4 5. Similarly for this 8, it can be 8 1 or 1 8. The probability is also 1 by 2 for this. So both are extremes. Extreme values, extreme by extreme I mean that they are at the ends. So I should write probability of ends. Ends are local maxima. So here you clearly saw that for this 5 and for 8 you have other numbers also. You can either write it 5 4, that means that 1 by 2 probability, and you can write it 8 1. There is again 1 by 2 probability. Now the middle number. So if you take some numbers in the middle, it should be local maxima. If you take this 4 9 2, so 4 9 2, how many permutations are possible? Because there are three numbers and it has to be there should be three places. So 3 multiplied by 2 multiplied by 1, that is 3 factorial, that is 6 total number of permutations are possible. So what are the permutations that are favorable to us? The favorable is 9 should be at the middle and rest you can do anything with that. So there are only two favorable permutations, that is 492 and 294. So now you have two possibilities which are favorable, and out of 6 possibilities, that means 1 by 3. The probability that middle numbers are local maxima. What is the probability? Clearly it is 1 over 3. Okay, so here I showed you this. So total number of permutations, if you just permute it is 3 factorial, that is 6. Number of favorable permutations is 2. 2 by 6 is 1 by 3. Okay, I told you, like, if you have to fill 3 places, you have to fill this with the largest number. So how many with what probability can you fill? So you can fill it 1 by 3 because there are 3 possibilities. Okay, so now you got these probabilities. Okay, now what I can do is I can introduce an indicator random variable, which we have been doing a lot once we were computing expectation. So I can say, let's suppose I of j be an indicator random variable, which will say that at jth position, if that is a local maxima, if it is a local maxima. Okay, it will take value 0 or 1 based on if it is a local maxima or not. So what I can write is, I can say expectation of I1 plus I2 plus and so on till in, expectation of all of these. So because I know linear to expectation, okay, linear to I can expand it. I can write it like this: expectation of I1 plus expectation of I2 plus and so on till expectation of in. That means I have, for total, I have to do this for n computation. So for this, what I am doing is, so I'll tell you that here we have n numbers. So n, 2 numbers are at the extreme. So those 2 numbers have probability 1 by 2. And for the other numbers, okay, I am doing computation for all the n things together. For all the n minus 2 numbers, they have the probability of 1 by 3. This is n minus 2 divided by, and now if I compute it, this comes out to be n plus 1 by 3. Check the answer. This is the expectation. Okay, you can just check it. So let's suppose if n is greater than 2, or maybe let's suppose 2 greater or equal to 2, because 1 doesn't make sense. 1 is a maximum always. So if there are 2 numbers, so this will be 2 plus 1 divided by 3. So there will be a local, there will be at least one local maxima. So if you have if you have 2 1, okay, how many local maxima? It's guaranteed that there will be one maxima. So you can put values over here. So this is 2 plus 1 is 3 divided by 3. This is 1. The expectation is one local maxima. Similarly, let's suppose for infinity, you have infinity, n is infinity. That basically means I have the sequence of infinite numbers. So naturally, the local maxima should also tend to infinity. So if I say infinity plus 1 divided by 3, this is also infinity. Okay, so this is some sort of checks which you can do. Is my expectation correct? Because if your n goes to infinity, obviously that your local maxima should also go to infinity. If you have, let's suppose, if you have a sequence of two numbers, 2 plus 1 is 3 divided by 3 is 1, that means you are expected to have just one local maximum. Any questions on this? Okay, now after all of these distributions, we'll move to Poisson's distribution. Poisson's distribution, as I said in the previous lecture also, this is the most widely applicable and mostly widely used distribution in the real world. Okay, most widely used. These people try to always come up with Poisson, they try to approximate with Poisson distribution. So here, the thing is that you again have have to model success and failure. So now, why does this Poisson distribution come into picture? So if you see this Poisson distribution, so you will see this if there are huge number of trials. So the number of trials you perform is very high and success probability is very low. Success probability is low. That is why you use this Poisson distribution. Okay, so you do a lot number of trials and the success probability is very low. Okay, let's suppose I'll give you an example. For example, number of accident on the road. So if you see a lot of vehicles are traveling there, but the accident probability is quite low. It's probably 0.01 because you don't see. If you have road, let's suppose I'll name that road. Let's suppose road number MG10, something of this sort. This is my road. So I want to compute the number of accidents that will happen there. Okay. Now you know that here we perform a lot of trials, but each day a lot of cars pass. Okay, passing of an event can have an accident. If two cars pass through each other, so they can have an accident. But you know the possibility of having an accident is quite low. So you can approximate it through Poisson distribution. Sometimes why is this Poisson distribution very widely used? Because it makes calculations very easy. So if you see binomial distribution, so you can approximate binomial distribution also using Poisson's distribution. So what will happen there? So in binomial you see that there is factorial term involved. Okay, but by using this Poisson distribution to make the calculations computationally very less intensive. That's why it's always almost preferred when it is binomial. So if you can approximate it using Poisson's distribution. So as I said, one example is you have huge number of cars passing by, but in each passing by there is a very low probability of an accident. Similarly, if let's suppose you have some earthquake, okay, you have some earthquake, so you know that there are a lot of days which pass, okay, and number of trials is very high, but happening of an earthquake is probably very low. There is a very less probability that on a particular day that earthquake will be there. Okay, and one example is also that let's suppose if you have a piece of land, something of this sort, piece of land, and there are, so you want to compute the probability that you want to compute the number of raindrops which will let's suppose drop on this piece of land. You have a piece of land which is 1 kilometer by 1 kilometer, something of this sort. But you know that this number of raindrops and is huge, and probability that hitting one square in this, okay, it's very low. It's pretty low because you know that rain is sparsely distributed. So again, this can be approximated as phenomenon. This phenomenon can be approximated as Poisson distribution. So only two characteristics are needed. So if there are huge number of trials, and the success probability of each trial is quite low. Okay, and one famous example that I saw is of chocolate chips. So when you have those chip cookies in which there are chocolate pieces in that, okay, that's also considered as a Poisson distribution. Why? Because let's suppose this chips is mostly made up of non-chocolate, and you randomly are getting chocolate in there. Okay, so you are making a lot of cookies in that. The N is quite huge, or the area is quite huge, but the chips you will get, there is a very less probability that each event will happen. That a number of cookies, a number of chocolates in this chocolate chips is quite low. Okay, now how to define probability mass function? Because as I said, that whenever you do something, whenever you define a probability, whenever you define some discrete random variable or in general random variable, you should come up with probability mass function or probability distribution or CDF, something of this sort. These distribution functions you can only come up with this. So this is only applicable to continuous random variable. This is applicable to discrete random variables. Okay, so here we'll focus on this because it's a discrete random variable. From PMF we can convert it to CDF. Now we want probability x is equal to k. Okay, that is, we want k success, the probability mass function. Here we want this probability of k. So I'll directly write the formula. The formula goes like this: e to the power minus k minus lambda to the power k divided by k factorial. So this is the probability mass function, and k here belongs to 0, 1, 2. This is the PMF. This is the probability mass function of Poisson's distribution. E to the power minus lambda power k divided by k factorial. Okay, this is the PMF of this. So here, in order to check this, so what you can do is, so you can say, does it follow the probability axiom? So is this greater than 0? It is greater than 0 for an instance. So that is sum up to 1. If you sum up from this, let's go from k is equal to 0 to infinity for all the values, e to the power minus lambda and lambda to the power k divided by k factorial. You can take this out. E to the power minus lambda can be taken out. This is summation of k 0 to infinity lambda k divided by k factorial. So if you know this, so this is the definition of or Taylor series expansion of e to the power lambda. This is Taylor series expansion of e to the power lambda, or sometimes it's called, it's defined that way. So if you have defined e to the power x, you define it like this. So this is e to the power lambda. So now we have e to the power minus lambda to e to the power lambda equal to 1. And now you saw that if you summation this over all the k, that is k 0 to infinity, the sum comes out to 1, and it is positive also. That is, it's a valid PM. The first thing is it is valid PM. How do we check that? It follows two axioms of probability at least. The first thing is it is non-negative, that is it's greater or equal to 0, and second thing, when you summation over all the possibilities, you get 1. Now how to compute expectation? So you have to compute expectation of it. So that is the standard thing that we do. We first define a random variable and then define its PMF, and then second thing what do we do is we compute its expectation. Can you compute the expectation? I'll give you 1 minute to do this. So now how to compute expectation? So expectation of x, let's suppose x is a Poisson distribution random variable or Poisson random variable. So this is a summation of k goes from 0 to infinity, k multiplied by the PMF of Poisson random variable. What is that? That is e to the power minus lambda, lambda to the power k divided by k factorial. So now what we'll do is we'll bring this e minus lambda out, because this is not dependent on summation. Bring it out of summation. This is k 0 to infinity, then k multiplied by lambda k factorial. So now here you can see this is k, this is k factorial. So you can expand this as k into k minus 1 and cancel out these k's. Take lambda, summation of k goes from 0 to infinity. I can start k from 1 also because this doesn't matter. And this is lambda k divided by k minus. This is equal to e to the power minus lambda. And if I see this, I can bring 1 lambda out. This will be k 0 to infinity lambda k minus 1 divided by k minus 1. But this is again the definition of for lambda. This is e to the power minus lambda to lambda. This is equal. So we got the expectation. It's pretty easy to remember. Expectation of Poisson distribution is lambda. So here this lambda is called as rate parameter. Rate parameter. So this is the parameter that we use in the PMF also. This lambda is a parameter of this, and it's called a rate parameter. I hope this expectation is quite easy. As I said, you can let's suppose take events which are a lot of events are there, so you can mathematically model this. As I said right now, loosely verbally over here, huge number of trials and success probability is quite low. So what can you do is you can write it mathematically. You have a lot of events. So let's suppose you have events E1, E2, E3 till En, and En is quite large. Okay, here n tends to, let's suppose, large. I should not write infinity, I'll write large. And even I can write infinity also. N tends to infinity, basically it's huge. And I can say probability of success, probability is P tends to 0. P is very small. It's very small, and the trials are very high. So this is high, huge number of trials and small probability. How I can write it math. Okay, now one more thing that you can assume here. Here in events can be independent or weakly dependent. So what is the meaning of weakly dependent? That means if there is very less information released, you cannot say more about it, but if there is very less dependence on this, so this cannot be mathematically defined. So weak dependence basically means if you can just have a minute clue about something, not the whole information, but a minute clue. So there is a dependency, but that dependency is very less. So events can be completely independent, you can still use this. If you have some weak dependency, you can still use this. Okay, there is something called as a Poisson's approximation or Poisson's paradigm, so where both this binomial and Poisson distribution are shown to be similar under certain conditions. I'll show you that. So we can write this Poisson's paradigm. This is also called as you are basically relating binomial to Poisson's distribution. So how to relate this Poisson's distribution? Okay, now you know that. So if I write binomial formulation, so probability x is equal, x takes value k. So you know what's the formulation? NCK, probability of k, q, n minus k. This is how do we define its PMF. Now what we have to do is, if I can just rewrite it. So here what I assume first is, I again assume that n tends to infinity. Okay, that means p tends to 0. You have a huge number of trials and p goes to 0. That is, you have very less probability of each success. So I'll assume that this lambda is equal to np, that is expectation for np. So this is the thing, because I want to relate these things. If lambda is np, the expectation of Poisson, this is equal to expectation of the binomial random variable that we have over here.
Hello. Hello.
So now I am sort of comparing here, where I am relating binomial distribution to the Poisson under the condition that there are a lot of trials and probability is very less, and I am saying that lambda is equal to np. So this is basically, I am equating the expectations of both these distributions. Now if I expand this, so you know the PMF of a binomial distribution is written like this: n choose k, p to the power k, that is success probability, failure probability, n minus k. So if I expand this, okay, I can expand it like this: n into n minus 1 into n minus 2 till n minus k plus 1, and divided by k factorial. This is the definition of permutations. If you can see, I can just expand it like this also. And here, over here, if you see this, so now what I can do is, these are my terms. So now I know this lambda is equal, and I'll just change p. So this is lambda is equal to np. So p is equal to lambda by n. I'll use this instead of p. I'll use lambda by n. So here I have lambda divided by n, that is to the power k, and then I can use this 1 minus p. This 2 is 1 minus p. 1p is lambda by n to the power minus k. So this is how I have done. Okay. Now if you see this, so these n terms are there. So if I now use limits, so if I use a little bit of calculus and limits, so this n tends to infinity over here. So if you see this, so here I have n tends to infinity and p tends to 0. So if I use limits there, so you'll come to know that these n terms will cancel each out. Okay, so you have n. So here you have, let's suppose this k factorial, again this will expand. Here you have, let's suppose, n to the power k. So this, if you see this whole term, it will cancel each other, because in the denominator you have also n, in the numerator you have n, and you have this k factorial. So let's suppose if you write n plus 1, let's suppose n to the power n plus 1. So here similarly you write n and n plus 1. So the plus 1 will not make much effect, but these n's will have high value and they'll cancel each other. So if you compute limits over here, so this will cancel out each other. So this will add 1. So now if I expand this, so I can write it in two ways. So I can write this 1 minus lambda divided by 1 minus lambda by n, this term 1 minus lambda by n to the power n multiplied by 1 minus lambda by n power minus k. So I have these two terms now. Okay. So this also goes to 1. Why? Because if you put limit, so lambda divided by infinity is again 0. So 1 minus 0 is 0. 1 raised to power minus k is 1. So this is again 1. So it goes to 1. Okay. Now if you use this, again, so this is again the standard definition of e to the power x. Okay. But here what you will do is, you will just, if you have done some problems on compound interest, so that is why you see the e to the power x. So if you can see, you just expand, we can get lambda to the power k divided by k factorial, and you get standard definition of power minus. Basically, so here I am somehow I am cutting down the steps. So here you will have to fill the bridge. So you will get a equation of some sort of compound interest equation, and you will fill that up with e for lambda. This is what you will get. Basically, the thing that I wanted to show here is that under these conditions where you have n that tends to infinity and probability is very less, binomial distribution or binomial random can be approximated. I'll write it. It can be approximated, not exactly equal. Can be approximated to Poisson distribution. Okay, and we can show graphs so that you also see all of these things. So we can plot the graphs also. Okay, let's do a question on this. So this question I'll basically tell you the question, and you will have to figure out the answer. If you are unable to do, then I'll do it. So we have done that birthday problem. That birthday problem was done. So in which you had n people, and I wanted to ask you what is the probability that at least 2 people share the birthday? How many people are needed, or something of that sort. Now let's suppose if you change this from 2 to 3. Okay, now you are not having a pair of people, you are having a triplet of people. Okay. Now if you are asked to compute the probability that at least a pair of people among the n people share a birthday. Here you have to compute the probability that at least one triplet rather, not pair, one triplet shared the birthday among n people. What is the probability of that? Can you compute the probability of this? So I'll give hints of this solution, and then you will at your leisure time try to solve it without seeing the internet. So the hint is, first you should justify that you can approximate this by using Poisson's distribution, Poisson random variable. Okay, you should justify that. Now you know that there is only one parameter, lambda, that is rate parameter. This rate parameter is there which you have to compute, and then you can just plug in the values in the equation of Poisson's random variable, and then you can come to solution. So how will this lambda be computed? This lambda can be computed by expectation. You have to compute expectation of something, and you will come up with this lambda, and then you will just plug and check value, you will get the answer. But first you should justify that this actually can be modeled as Poisson's random variable, and you will have to give proper assumptions of that, and then you can compute expectation, then you can fill in the values. Please. Okay, with this I'll stop this recording, and I'll sort of close discrete random variables here, except this question, and 2-3 things are left. And I have told you to I think prove linearity of expectation, and I have told you to prove expectation of maybe hypergeometric random variable or something. So these were the homeworks that I did, that I gave you, and one more homework that I'm right now giving is this question.